All right, 1.4. Simplify as much as possible. So the square root of a number is the same as I. Hold on. The square root of a negative number is the same as I times the square root of that number. Now, what goes into 99? 11 and 9. 3 and 3. Can I pull anything out? A 3. So you take a set of 3's and you write it on the outside. So 3i, and what's left? 11. Do you know why that works? So, yes. And you're right, but I don't know that you quite get it yet. What we're doing is looking through and seeing, does 99 contain any perfect squares? What are the perfect squares? 4, 9, 16, 25, 36, and so on. So basically we're asking, do any of these numbers belong inside that 99? If they do, then we're going to square root that chunk and then leave the rest underneath. So this is what we did. You didn't realize it, but we did the square root of 9 times 11 times -1. Right? Well, what's the square root of 9? 3. What's the square root of 11? The square root of 11, that's an 11. What's the square root of -1? I. That's all we've done, and nobody's ever taught you that before. So that's why we circle a pair. What is the square root of 3 times 3? 3. What's the square root of 7 times 7? 7. That's why it works. What if it was a third root? Then you have to have 3 of them. Why? What's the third root of 2 times 2 times 2? 2. Third root of 8 is 2. Okay? All right. So, look at number 2. What is the square root of -25? 5i. And the square root of -5? I root 5. Okay? But last year you learned you're not allowed to leave an irrational number in the denominator. So, to get rid of the root 5, I times it by root 5. Is that legal? As long as you do it on the top. Now, why is all of a sudden that legal? Why does that rule work? What is this number here? 1. And multiplying by 1 doesn't do anything. Well, if it doesn't do anything, then why do we bother doing it? Right. So, how many different ways are there to write 1/2? An infinite number, right? And we have settled on a system that allows us to all come to the same conclusion, which is get rid of all the common factors. Simplify. The same is true of square roots. There are an infinite number of ways to write this answer. But if we follow the rules of rationalizing the denominator, then we will all come to the same exact conclusion. So, this... Wait, what? Okay, so I cancels I, and square root cancels square root, so I get 5 root 5 over 5. And then the 5's cancel, and I get the square root of 5. Now, is that better or worse than 5 over root 5? That is more simple, right? That's why we rationalize the denominator, because this form is more simple. It won't always end up looking like that, but that's the purpose. How do we multiply square roots? we multiply what's on the inside and then we simplify. So square root of negative 36. Well, we're going to factor 36. What does it factor into? Oh, 3 and 12. So we might as well just factor the 12. And then we look for pairs. Here's a pair of 3s. Here's a pair of 2s. So I get 6i times the square root of nothing's left. The answer is just 6i. The 4 factored, so we ignore it. Anything that factored gets ignored. Yeah, the negative turned into an I. Good question. Okay. All right. Adding imaginary numbers. All you do is combine like terms. So every complex number has a real portion and an imaginary portion. You just do, oh, wrong problem, sorry. Real plus real is 7. Imaginary plus imaginary is imaginary, and that's the end. And just for your information, we call this imaginary and this real, and we call this complex. Now, you could call the whole thing imaginary, but technically that's how we define them. Now, multiplying is a bit of a problem. So, I put my box together. 2 minus 4i, and 4 plus 6i, 8, negative 16i, 12i, and negative 24i squared. So 8, and then these two go together to create negative 4i, and then negative 24i squared is just positive 24. And now I need to stick those together because that imaginary piece became real. Does that make sense? You want to see another one? Okay. So, negative 12 plus 8i plus 9i minus 6i squared. Do you follow that? Well, those combine to be 17i, and this is really just 6. So that is really just plus 6, and that joins with the 12, like that. Oh, yeah, because it got added to negative 12. It is, nope, it is negative. Negative 12 plus 6 is negative 6. Okay. What about this problem? I to the 53rd. No, your calculator won't do it for you. Nice try. So Kegley's got a good idea. Every pair makes a number, but it actually, you could do it that way. It actually goes through a 4-part rotation. So I did it again. I equals I, which is also known as the square root of negative 1. So I squared would be this to the second, which is negative 1. And then negative I to the third. How would you get I to the third? You could do the top one 3 times, but it would be easier to do the top one and the second one. So negative 1 times I is negative I. And then what would I to the fourth be? It would be 2 copies of this, which turns it into 1. And then what would I to the fifth be? It's just going to be I. So there are lots of ways to do it. You could do a 1, you could do a 1 and a 4, or you could do a 2 times a 3, a squared times a third. It's just I. Well, what's I to the sixth going to be? Negative 1. And I to the seventh? Negative I. No. Oh yeah, and I to the eighth is just 1. So do you see how it goes through this cycle 4 times? Oh. So Kegley says, say it louder. So if it's divisible by 4, what is that? 1. How do you know? How do you know it's divisible by 4? It ends in a 32. If the last 2 digits are divisible by 4, then the whole thing is, because 4 goes into 100. So if it goes into 100, then it goes into 104, 108, 200, 204, 208. So this one equals I. What about I? Oh my goodness. 1, sorry. What about I to the 53rd? Well, let's just divide by 4. So I take my calculator and I do 53 divided by 4, and I get 13.25. So it's not divisible by 4, but what is the remainder? What's the remainder on this division? It went in 13 times remainder 1. How do you know? It's 1/4. So it must be the same as this, because the remainder is the same. It's not divisible by 4. The 0.25 is the same as 1/4, which means I went through 13 cycles and 1 step further. So if I had I to the 67th, 67 divided by 4, how far over did I go? 3. So it must be the same as I to the third. Okay? So if your decimal is 0.0, that is the same as I to the fourth, which is 1. If your decimal is 0.25, that's the same as 1/4, which is the same as I to the first, which is I. If your decimal is 0.5, that is 2/4, which is the same as I squared, which is negative 1. And 0.75 is 3/4, which is the same as I to the third, which is negative I. So all you need to do is divide the exponent by 4 and then figure out what the remainder is. If it goes in evenly, the answer is 1. If you get 0.25, the answer is I. 0.5, the answer will be negative 1. And 0.75, the answer will be negative I. Yeah, so that's a good point. Do I care how many cycles I go through? No. So basically, we're doing this. We're doing 1 whole cycle, 2, 3, 4, 15, 16, remainder 1, 2, 3. So the number of cycles is irrelevant because it starts over every 4th time. So all you need to look at is the leftover. Whoa. Where did that problem come from? I'm going to get rid of that problem. That should not be there. One of these things is not like the other. Okay.